So this is chapter 4. Chapter 4 is exponents and logarithms. The first section is talking about inverse functions. The reason why I talked about inverse functions is because exponents and logs are inverses of each other. We'll mostly do just A, B, and C. We'll talk briefly about D and E, but really mostly just A, B, and C. So we have to talk about what a one-to-one function is because inverse functions are one-to-one. So that is where we will start. So a one-to-one function is where every element in the range corresponds to only one element of the domain. So range, domain. So that is the opposite of what a function says. A function says every element in the domain corresponds to only one element of the range. So what we first have to note, though, is that this is a function first. It's a function first. So it is true every element of the domain corresponds to only one element in the range. But then it's also true, because it's one-to-one, every element in the range corresponds to just one element in the domain. So range, remember, is our y values. Domain is our x values. So what that says is that if you think about your x values and your y values, because it's a function, x cannot repeat. Because it's a one-to-one, now y cannot repeat. So no repeats. X and y, nothing repeats. One-to-one. So one x goes to only one y. One y goes to only one x. That's what that's saying. So to determine if something is a function, we can use a vertical line test. And then since that's switching for one-to-one, to see if something's one-to-one, you can use a horizontal line test. So it works the exact same way as a vertical line test, just instead of vertical lines, you're doing horizontal lines. So we'll look at these graphs and see which one is one-to-one. So we're already saying it's a function. So these are what we know are functions. We're looking at the red. The blue lines are just indicating an interval that we're looking at. So the red is what we're looking at, the graph of the red. So I know this is linear. I know that's a function. But I want to know, is it a one-to-one function? So I take your pen or pencil and look to draw horizontal lines. Okay, so do any of these horizontal lines go through the graph more than once? No. So yes, this is one-to-one. And I usually write 1-1 to indicate one-to-one. Okay, here, this red is quadratic. Okay, well, quadratics are functions. It would pass the vertical line test. But does it pass the horizontal line test? No. So even though it's a function, it is not one-to-one. So not every function is one-to-one. And if you think about every every element of the range only has one, corresponds to only one element of the domain. I have 4 is my range element, and 4 corresponds to 2 and negative 2. So that means that it's not one-to-one. So this says use horizontal line test to determine whether each graph is a graph of a one-to-one function. So just a quick overview. This is a function. This is a function. This is a function. And this is a function. So all of these are functions, but I want to see if they are one-to-one functions. So use horizontal line test to determine if they're one-to-one. So A, is this one-to-one? Yes. Yes. Okay, what about B? Is this one-to-one? Yes. So it approaches this, x-axis is an asymptote. It approaches, but it's getting closer and closer. It never gets exactly horizontal there. So this is yes. Okay, what about C? Is this one-to-one? No. What about D? No. Okay. All right, do you understand the difference between functions and then one-to-one functions? Okay. Functions, vertical line test. One-to-one, horizontal line test. It's possible to be a function like C and D without being one-to-one. Okay. All right. So let's talk a little bit about inverse functions. So I have f of x, and then I have its inverse, f inverse of x. So we'll talk more about that notation here in just a minute. So this f with this little -1, when it's between f and x, that's saying inverse. So it's not an exponent, it's f inverse of x. Okay, so this means you say f you say f inverse of x. Okay, so let's make a table for f of x, so our given function, just plug in these values so we can find the y. Plug in those x values and find the y values. Should take just a second. -11 and then -8. Let's go ahead, fill the rest of that table out. what you guys got. Okay, so I'm going to do the same thing down here, but I'm going to be specific about my x values. So I'm going to take my y values and now plug those in for x. When you go to plug those in, if you're using your calculator, either put parentheses in the numerator, or you, after you add 2, hit enter before dividing by 3, because that numerator needs to be done first. So what you're doing is negative 11 plus 2 divided by 3, so that's negative 9 divided by 3, which is negative 3. So just make sure you calculate the numerator first. So go ahead and fill in your y values. Okay. So what do we notice? Yeah. So your x and y coordinates switch. So all these domain values in f of x become your range values in f inverse of x. So that's a property of inverse functions. Your x and y's will switch. So we summarize that here. So what we note first is that f is one-to-one function. So you have to start with a one-to-one function. It has ordered pairs A, B. Then the following is true. So if f is a one-to-one function, then f inverse of x is a one-to-one function. And your ordered pairs switch. So they go from A, B to B, A. Then your range becomes your domain becomes your range. Okay. So f inverse of x does not mean reciprocal. So when the negative 1 is here, between your f and your x, it is not an exponent. So that means inverse, not an exponent. So what we mean about reciprocal is that if you do 3 to the negative 1 power, that's 1 over 3. This negative 1 is an exponent. But this negative 1 is an inverse when it's in function notation between your f and your x. That means inverse. Okay, the next thing we're going to do is find an inverse. So find an inverse algebraically. So here are the steps that we're going to use to do that. So what I'll do is use y instead of f of x. It just makes it a little bit easier when I do step 2. Step 2, I will switch places with x and y. And then I'll solve that equation for my new y. I want to try to get that new y by itself. Then I will replace f inverse of x with that new y. Okay, so I'm going to do this problem here. And I'm going to graph it as well, even though it does not tell me to graph it. I'm going to go ahead and do that. So first thing is I want to find any 3 ordered pairs for f of x. So I'm going to make a little table for my f of x. I'll go ahead and I'll just do -1, 0, and 1. Plug in -1, 0, and 1. So I should get -4, -5/2, and -1. Okay, I'm going to graph those points. So this is a linear function, and it looks a little different, but if you were to divide both terms by 2, you would have a slope and a y-intercept. It would be mx plus b. So this is still linear. You don't have an x in the denominator, so all it is you're just dividing by this constant. So this is a linear function. But I'll graph those 3 points and draw a line. I will explain what this red line is here in a little bit. So you can ignore it for now. Okay, so -1, -4. Zero, -5/2, so that's -2.5, and 1, -1. Okay, draw a line. Okay. So this is f of x. Alright, so this was part A. Part B, we want to algebraically compute f inverse of x. So that's where I'm going to go through these 4 steps. So step 1 was to write y instead of f of x. interchange x and y. So switch x and y. Step 3, solve for the new y. Okay, so I'm just going to write this down. I want to get that y by itself. Well, the first thing I need to do is move this 2. I'm being divided by 2, so what do I want to do to both sides? Multiply by 2. Okay. So then I get 2x equals 3y minus 5. So I'm trying to get y by itself. So what would I want to do next? Yep, add 5. So 2x plus 5 equals 3y. And then what? Divide by 3. So I have 2x plus 5 divided by 3 equals y. Okay, step 4. Replace your new y with f inverse of x. So f inverse of x equals 2x plus 5 divided by 3. Okay. So I'm just dividing by a constant. So what type of function is this? Yeah, this one's also linear. So I'm just going to make note about that. And I'll graph it. But it wants me to, this is part C here, verify the ordered pairs satisfy f inverse of x. So, what do I need to plug in for my x values? Right, I'm plugging in the y's for x. I'm verifying that when I do that, I get these original x values. So -4, -5/2, and -1. Plug those in. In your calculator, if it's easier for you to plug in -2.5 instead of -5/2, that's fine. You're plugging it into f inverse of x. Okay, 1, 0, and 1. So I verified that was correct. So this is a way to check if your inverse is correct. If you've calculated that correct, plug in some points to the original, and then make sure that your y values, if you plug those back in for x in the inverse, you get the x values. Now you can check to see if your inverse is correct. Okay, so I'm going to graph these points now, and then I'll draw the line. So -4, -1, -5/2, 0, and -1, 1. Okay, so then this is f inverse of x. Okay, so that red line, this is the line y equals x. So what happens is that inverse functions reflect over that line, and that's because you're interchanging x and y. So this line here, y equals x, is a line of reflection from your original to the inverse. And you're not going to be asked to do that, but it can help you if you are graphing these to kind of picture in your mind what it's going to look like when you do the original and the inverse. So So this just means that y equals x is you start at 0, your y-intercept is 0, and then your slope is 1, so up 1, right 1. Yes?
So is the parent function the line of reflection?
No. The parent function would be like f of x. And then, but the inverse isn't, it is a reflection over that line y equals x. So, f of x was linear, and its inverse was also linear. Well, that's not going to be the case for all types of functions. So if you think about what it means to do an inverse, so if you're quadratic, you have x squared. What is the inverse operation of x squared? It's the inverse operation. Yeah, square root. So the inverse function of a quadratic is a square root. Okay, so those don't look exactly the same. The reason why linear was so linear is because all these inverse operations I was doing were just transformations. You're just adding, subtracting, multiplying, and dividing, but you're not doing an opposite main operation like square and square root. Okay. Okay, so let's look at this. We'll just get this started, and then we'll have to stop. We get out of here at 11:33. So f of x is x squared minus 2. So I know that f of x is quadratic. And that minus 2 means it shifts down. So the minus 2 would need to be inside the parentheses for it to shift right. So shift down 2. Okay, so that means my vertex here is at 0, -2. And then from the vertex, you can do that squaring pattern. So over 1, up 1 on both sides, over 2, up 4. And then from your vertex over 3, up 9. Okay. To help us graph the inverse, I want to put these points in a table because then I can just switch my x and y. So I'm putting these points here. So 0, -2 was the vertex. I have the point -1, -1, 1, -1, 2, 2, and -2, 2. -3, 7, and 3, 7. Okay, I want to do f inverse. I'm going to switch all these x and y's. I will graph those. Okay. All right. And then we need to talk about this, which we will more tomorrow, because we have problems here. The inverse, that's in blue, that's not a function. And the reason why it's not a function is because f was not 1-to-1. So that's where we have to talk about that it's important to be 1-to-1. So we will talk more about that tomorrow. I hope.